Okay, good afternoon and welcome to the GridWise Architecture Council's tutorial on fundamentals and terminology and concepts driving the grid future states. Welcome. We'll be in this room for the next few hours. Roughly 3 hours is what we have planned. We might be done earlier than that, so get yourselves comfortable. And again, thank you all for coming today. Good turnout. We appreciate that. We also appreciate the partnership that we have with REplus. You'll hear a little bit about who the council is, and we'll have plenty of time for some questions and discussion after each one of the different sections. We have 5 different speakers today, so that's our basic format. I'll go through a little bit more of that in some detail here. See, I'm going to try to. There we go. Okay, so let me introduce myself first. I'm Ron Bernstein. I am the council chair for the last couple of terms. I am also a consulting engineer, a mechanical engineer by trade, and I work for a company called RBCG Consulting. It's my honor and privilege to be elected as the chair, taking on a big motley crew. It's kind of like herding cats from all the different industries, so we appreciate everyone who's participated in creating the events here. So a little bit more detail about the council. How many folks in the room are familiar with the GridWise Architecture Council? Who's never heard of it before? Everybody in the room. Okay, well, this is good. So the GridWise Architecture Council, and I'm just going to read this right here. It says it's a team of industry leaders who are shaping the guiding principles or architecture of a highly intelligent and interactive electrical system, one ripe with decision-making, information exchange, and market-based opportunities. This architecture will provide guidelines for interaction between participants and interoperability between technologies and systems. That's kind of a mouthful. So what we did is we said, all right, we're going to make that a little easier. We'll show you a little video in a minute. But we are a supported activity and partially funded activity by the U.S. Department of Energy. So U.S. Department of Energy works with Pacific Northwest National Labs. We have Jamie here from Pacific Northwest National Labs as our administrator, and then we have this 13-member council that is elected by industry as volunteers. We're all volunteers to shape the grid architecture and principles around the North American power grid. So what we did is we put together this is the introductory first unveiling of a short video that describes who we are and what we do. So I'd like to play that for you now.
Who is building the grid of the future? Well, there's no single organization. The task is just too big. But the GridWise Architecture Council is shaping the guiding principles or architecture of a highly intelligent and interactive electric system. The Council offers concepts and guidance to stakeholders who are part of the evolution of the power grid. Convened in 2004 by the Department of Energy, the GWAC has already had a big impact on interoperability standards and transactive energy concepts. The Council envisions the societal benefits of a decarbonized, decentralized, and democratized electricity system that will supply the energy needs of today and for future generations. The power grid is evolving. New technologies generate, control, and use electricity. And coordinating these distributed, sometimes customer-owned, assets is complex. The GridWise Architecture Council guides this evolution and promotes interoperability among the many entities that interact with the nation's electrical power system. The 13 rotating council members have a variety of backgrounds within the electrical system. They are thought leaders in utilities, buildings, policy, engineering, software, consumer advocacy, and more. The Council bridges these communities with their individual perspectives to create an inclusive vision for the future grid. This guidance facilitates the interoperation of the systems, devices, and institutions that encompass the nation's electric system. To prepare for the grid of the future, the GridWise Architecture Council defines, clarifies, and recommends architectural principles and concepts. and provides guidelines, position statements, and checklists for decision makers. Workshops and meetings identify challenges and solutions and provide feedback to the Council. The Council seeks input from various sectors and stakeholders to create a consensus vision for the future grid. If you're interested in helping shape the vision for a decarbonized, decentralized, and democratized electricity system, we'd like to connect with you. Get started by joining us for GWAC monthly meetings, which are listed on our website.
There you go. Big round of applause for the PNL folks who put that together for us. Thank you. I thought that was a good job. That just rolled out this week, so we're very excited to have that. Whoop. Hey, stop that. There we go.
So excited to watch again.
Huh? What's that?
So excited we'll watch it again.
We'll watch again. No, we won't watch it again. So as you can tell, the GridWise architecture has been around for a while. In fact, we're celebrating our 20th anniversary this year. And in fact, we all just got pinned just a few minutes ago and got our 20th anniversary pins on. So we're very excited about that. We have a celebration happening this Friday down in San Diego after the conference here. But today, let me talk a little bit about what's happening here at REplus in regards to GWAC and our activities. So on Wednesday and Thursday of this week, we're holding the GridWise Architecture Symposium. You'll hear a little bit more about that later. That's a 2-day event. It's open to anybody. If you learned some things today, you might want to participate in that. I think we have well over 25 speakers that are going to participate in that 2-day symposium, keynoted by Gene Rodriguez from the U.S. Department of Energy, number 2 at the DOE. Number 2, do I have that right? Yeah, number 2 at the DOE. That's going to lead that off on Wednesday. I'll show you the schedule in more detail in a minute. If that's something you're interested in attending, I did bring about 70 flyers that give the information of where it is, when it is, who's speaking when, and the room numbers. So if you'd like that, see me afterwards and I can get you a copy of that. But in order to understand some of the concepts, we thought it would be a good idea to hold a tutorial. And this tutorial is really an educational session to talk about some of the terminology, some of the concepts that evolve into what we talk about with grid architecture, transactive energy, distributed energy resource impacts on the grid. So we thought we'd take a little bit of time and bring maybe the novice or the not well acclimated into that terminology up to speed in this next few hours. So that's the purpose of today. Again, a free sponsored session by the council. So this is our agenda. It's going to be a little hard for some of you to see that, but we'll go through it in detail. We have 6 speakers that are going to come up, and they're all kind of circled around up here, all council members and administrators that are going to share some of their wisdom with you. So I won't go through the entire agenda here, but you'll see that. We'll take a break after, I think, session 3 for a few minutes. So I want to introduce our speakers. I want to introduce everybody now, and then everybody can come up one at a time later. So again, I'm Ron Bernstein. I'll be moderating today. We have Ron Ambrosio. Say hi, Ron. Ron is our, I want to say our oldest, but our longest standing GridWise Architecture Council member, who's been involved since really the beginning. They're signed on as the original charter. So we're glad to have Ron. He's now retired as a consultant. We have Kay Aiken from Dynamic Grid, one of our newest members, who will be sharing some insights into what her perspectives are. David Forfia from Utilicast. David, want to raise your hand over there? There's David Forfia from Utilicast, Farouk Rahimi from OATI, and Jamie Colton from PNNL. So that's our speaker list for today, and we really appreciate all of them taking the time not only to create the content for you all, but taking time out of their schedules to come be with you today. And again, everybody's a volunteer here, except maybe Jamie. So I'm going to lead us off. I'm going to talk a little bit about bridging back from the future and the future state of the grid. And I'm also going to talk about the 25-year event horizon for the North American energy usage and electrical power grid. So a little bit about my background. I'm in the buildings market. I'm a control automation guy. Sometimes people call me a control nut, but I'm out to control the world one device at a time. So as part of that, we're learning in the buildings market that building to grid interactivity is crucial in the way we design and implement our energy structure. So I'm the buildings guy on the council. So when we talk about building, one of the challenges that we've identified is where does the grid need to be in, let's say, 25 years, and how do we get there? And we call that bridging back from the future. So if we say what the grid is going to look like, and we're going to start implementing technologies and methodologies, which we'll talk about, where is it we're going, and are the things we're doing now going to get us to where we think we need to be? Rather than just saying, well, today we think we're going to do this and tomorrow we're going to do that, well, let's set a stake in the ground and at least work to some common objectives. So a lot of what we've been working on in the council for the last few years is about this concept of where is the grid, how is the energy market and energy requirements for North American changing, and then how can we affect that change in a more positive way. So if we work towards this 25-year event horizon, we start looking at what do we think the market is going to require? What are the step changes that are needed? If we keep doing what we're doing today with the incremental changes in the way we consume and produce energy, are we going to have a stable grid in 25 years? Most people would probably say no. We're already seeing that. So just yesterday, anybody here from San Diego? Besides myself? Nobody here from San Diego? Okay. Oh, one from San Diego. Did you guys have a blackout yesterday?
I actually was here.
Oh, you were here. You're lucky. So I had another workshop at my house yesterday. We had 65 people in my house for a workshop, and SDG&E decided, no, it's too hot, we're going to cut power. So we didn't have power for the first half of the workshop. We also didn't have power on Friday and Saturday. 3 days in a row, we were out of power for 5 to 6 days. That's really not a conducive way to run our power grid. We understand it was 100 degrees outside. We understand the safety factor, but at the same time, how do we manage that? Now, I have solar on my house, but I don't have batteries. But I do have a generator, but I didn't kick on the generator. So there's all these things that factor into what are those changes that are required in order to make the grid more resilient, more reliable, and adapting to our usage and needs and weather and social impact. So we have to define something that is achievable, believable, and acceptable. We'll talk a little bit more about that. But when we define that 25-year event horizon, we have to kind of say, yeah, that's reasonable. We'll be able to do that. Or this is what we believe is the state that we're going to be in 25 years, and we have some real challenges to get there. So what are the market conditions that need to get across the bridge? Now, very often, even in the council, we talk a lot about technology. But technology doesn't solve all problems. We also need to consider the value, the cost, and the implementation methodology that we're going to get there. So market conditions often leads to how do we define policy and regulatory requirements in order to get across that bridge. And we have to change our thought process in order to get there. So we also have to define who are the stakeholders. Is it just the utilities? Probably not. We're here at REplus. More than likely, it's going to be someone who's dealing with something related to renewable energy. So the stakeholder list is growing. Those concerns are growing. And what's beyond that 25-year event horizon? What about the next 50 years or 100 years? 100 years ago, if we said, hey, what's our stake in the ground for 100 years? Is the North American power grid going to be reliable, resilient, and be able to serve in an effective way? I would bet 100 years ago, we probably would have said no. Well, we're still using that same 100-year-old or older technology today, and we can see the effects of continuing that down the road. So let's look at a couple of other industries that have had some step changes. And when I say step changes, this is the difference between an evolutionary process and a revolutionary process. Evolution is small things that happen slowly that you can barely see over many millennium. Step changes or evolution or revolution is something massive happened. A meteor hit the Earth and the dinosaurs were wiped out. That was a massive event. Step changes in the industry, in various industries, have had monumental changes almost overnight. The horse and buggy moving to the automobile, How many folks still ride a horse to work? Anybody still? 100 years ago, you would? You do? All right, we still got one here. Yeah. Candles, kerosene, gas lanterns go to the electric bulb. So I'm just going to put up a couple of them here. One of my favorite ones, brick and mortar libraries. How many folks have been in a library in the last 10 years? Anybody been in a library the last 10 years? Last 5 years? Last 2 years? This year? Okay, that's good. I'll bet in a few years there are not going to be as many, but we're finding other ways to do the same sort of thing. I personally like the library, but anybody use Libby? Any Libby fans here? Excellent tool, excellent tool. So we're changing. How many folks still have a house landline? Oh, I got one, got two. All right, all gray hair guys. Yeah, rotary, no, he's on rotary now. No, still the push button dial tone, POTS telephone line. No, most everybody has a cell phone now. I really, believe it or not, I still have a landline in my house, only for one reason, is that I still have to communicate to a building that has an old dial-up telephone in order to do some programming on it. Not that I want to, but I have to, and this is for security gate programming. So a few others, fax gone to email, typewriter to personal computer, taxi drivers to Uber and Lyft. That's another one. Passenger rail to airplane. When was the last time somebody took a transcontinental trip on a rail? Anybody ever done that recently? Yeah, about 7 years ago. Not many. It's a fun way to travel, but certainly more efficient. Newspapers to online news, you get the idea. Those are examples of step changes. So as the element of change, we need to modify our philosophy. What is the philosophy that we're working towards, and what's important now? That drives most of the decisions we're working on. Where does that come from? It comes from societal changes. What is important to us now? Well, a lot about greenhouse gas, or a lot about climate. So why is that driving policy? Well, it's being able to respond to market demands and engage with more and different stakeholders than we used to, at least for the electric grid. Philosophy leads to psychology. Once we set our philosophy, oh, this is important, these are the things that are important to us, we then have to engage with the stakeholders and with the market on what can we change. And that's done through the regulatory process and through programs. Very often we put our money where our mouth is. The psychology about change comes in through regulatory and programs of where we spend money and where we tell our regulators how to work. And the last one, which we often get hung up first on, is the methodology. Methodology is how do we do this? Well, often we throw technology at it. How many technology folks in the room? Lots. Yeah, I would imagine lots. Any policymakers in the room? See, we need more of those. We need more policymakers. How about regulators? Anybody in the regulatory world? Yeah. It would really be nice if we had regulatory and policy at the same time and equal portions with technology, but we don't. So we have to continually think about how we get from point A to point B. So let's talk a little bit about some benchmarks, a little kind of history lesson. A little hard to see, but let me just describe this. This is a chart that I stole from some website at the U.S. Energy Information Administration from 2020. This is the energy consumption by energy source. We're still high on petroleum and natural gas. That's the red and the blue. And if we look at our renewable energy, it's only 12%. And if we look at within the new renewable sector, we're only at 11% of that is solar. So if we look at all of the different factors and what's changing here, the renewable energy market is growing, but it's still a blip on the radar. So if we look at the electricity production and we look at the amount of solar or wind compared to everything else, it's still pretty minimal comparatively. And if we look at where investments are, these are investments by government agencies or utilities, the investments are still going into some of the newer sectors, wind and solar, but we're not really affecting too much change yet. But we're heading in the right direction. So that's at least some indication of the direction we're going. So if we're going to do our 25-year event horizon, we need to find a way to look over that horizon and say, what is believable, achievable, and realistic, or believable, achievable, and acceptable, and put some sort of stake in the ground today to say, hey, we have a better than even shot of getting there. And these are some of the things, these are my personal opinions, not the opinions of the council, but I do believe that we're going to get to some high level of reduction of fossil fuel as our primary energy source. 25 years, can we get to 90% reduction? It's a good stake in the ground. Grid architecture shifts to primarily distributed systems. We're going to talk about what a distributed system is versus a centralized system, but we're going to shift more towards a decentralized or an infrastructure that allows us to put on more distributed systems than centralized systems. The grid upgrades focus on distributed energy resources and utility generation as equals. So if I'm behind the meter and utilities in front of the meter, I can put my energy out onto the grid and use the same distribution transmission lines to effectively enhance the amount of power available on the grid. Talk quite a bit more about that. We have some great examples of that. Transactive energy systems may become common across all sectors. Transactive energy meaning that I transact with you through something of value. So we often say, what's the price of an hour of electricity? What's the price per kilowatt? And we'll talk quite a bit about transactive energy and what that means. Maybe, this is my big hope, safe fusion-based technology or energy sources are demonstrated. If we can get there in 25 years, that would be great. Some people think that we'll be there sooner. Others are a little skeptical. But I say let's shoot for that. That would be a good thing. No coal-based energy sources on U.S. grid. Well, I'm not sure we'll get to that, but again, that's another, another vision. Natural gas resources reduced from 50 to 50% from 2020. Grid load increase. This is the one we often don't talk about. Is how much energy are we going to be demanding? Well, if you look at the demand, and we'll go back to that other slide, the demand, let me put back for that for just a second. If you look at the demand over time from 1950 to maybe around 2000, it's been steadily increasing. But then we look at from 2000 to 2020, and we're starting to see a relatively flat demand cycle. Do we think it's going to continue that way? Well, if we're going to electrify transportation, if we're going to electrify heating and air conditioning, if we're going to electrify buildings, my guess is no, we're not going to be there. We're going to need a whole lot more energy, and that's where I say maybe 20 to 40% increase in the overall energy consumption. And continued electrification of buildings, cars, and transportations will help us, make sure that we're planning for that. So that's my 25-year event horizon. We've talked about it in the council, relatively reasonable, believable, achievable. Maybe this will help us get to where we need to go. All right, so we then say, all right, if we're going to set that as our 25-year, what's our 15-year look like? Well, here's our 15-year. So here's a potential stake in the ground for 15 years. 15 years is not that long. I won't go reading them all. You can kind of see them there. So if we look at where we are now in a 10-year event horizon, well, 10-year event horizon means that we need to start implementing things now that are going to be effective and online in 10 years. So here's our reduction in increase in solar, coal usage reducing, our 5-year event horizon, which is like right around the corner. This is today. Increase in EV. How many folks in the room have an electric vehicle? How many folks in the room have a plug-in hybrid electric vehicle? Okay. Anybody trading up this year? Planning on trading up? Yeah. Yeah. Here we go. Electrification of cars. Does that reduce our greenhouse gases? Well, depends upon how you look at that. What's the source that's producing the energy that's charging your car? If it's coal, maybe not. If you're going to increase the amount of coal that you're burning in order to charge your electric vehicle, we might have that flipped around a different way. So again, my thoughts. So here's a stake in the ground for a 5-year event horizon, and then we start looking at the ways that we're going to not only produce energy differently, but the ways that we're going to consume and conserve energy. A big factor has to be about the conservation. So conservation, and again, I'm a buildings guy. Here it is. There it is. I'm the buildings guy. I'm the guy running around with the hard hat and the PPE. How many folks know what PPE stands for? Personal protective equipment. All right, a couple people there. So that's me there in my hard hat. This was a couple of weeks ago on a job site. And I say, why am I here at REplus or working with GWAC? Well, the reason is that the built environment, the building that you're in here, plays a significant role in the potential effective change that we can make in the 25-year event horizon. Buildings are the largest consumers of electricity as per capita of the different sectors, whether it's manufacturing, commercial, industrial, residential, and the systems that are involved, HVAC, refrigeration, rooftop solar, plug load, all of those things factor into how a building can be part of this ecosystem. And then we start talking about our own resources that we can put online. We can put on generators. We can put on microgrids. We're going to hear quite a bit about microgrids coming up here in a minute. So how all of that factors into the future of the built environment is a big part of the work that I do and try and bring into the council. And then grid-connected buildings will require reliability. I talked about this from my workshop that we had at my house yesterday. It got really hot after 60 people in my main area living room after about 2 hours. Fortunately, the electricity then came back on and we were able to cool down, but we're thinking we might have to send people outside at 100-degree weather because it got too hot inside, and we had no fans, we had nothing. And I didn't turn on the generator, which has to be plugged into the driveway. So there's a lot about the building to grid trajectory that we're looking at as a way of affecting change, where we have better control from individual buildings to smart buildings to grid-aware buildings. I won't go through all the detail here, but you get the idea that we've got resources we have to contend with on the demand side. We have transactive energy that we have to work with between buildings and between the building and the energy provider. We have the ability to communicate the status of what's happening in an environment and the ability to react to grid changes. So all of that factors in. I like using this model from the folks at P&L, and I call on Jamie. Where's Jamie? There's Jamie. Jamie and I are big energy service interface guys, which say that the building can be an interface for the grid. In fact, we wrote a white paper called Smart Buildings as a Transactive Energy Hub, which focuses on how a building can react and respond and be a partner with the grid. So behind the meter affecting change in front of the meter. So smart buildings have a lot of control capability. I'm a controls guy. So all of those different systems that you see down here all have the ability to react and interact with grid services. Demand response, load shedding, bringing on DERs as needed, and be able to react and respond as long as we have something called interoperability. How many folks have heard that word before? Interoperability, thrown around into in the market. What about open systems? Anybody hear about open systems? A lot of people talk about interoperability and open systems. In the council, we take a lot of effort, and really early on, at defining what interoperability and the ability for things to communicate with each other in a way that can effective change without locking into proprietary or closed architectures. So there's the link to the Smart Buildings as a Transactive Energy Hub. If you go to the GridWiseAC.org website, you can download that, and that's specifically about this topic. So smart buildings relates to how can we make change, and we'll get there with transportation as well and others. So let me, and here's our transactive energy systems and how we use energy systems interface or services interfaces to connect the building to the grid. So I'm going to stop there. That's the end of my pitch. Hopefully that gave you a little bit of a background. Let me just do a quick check. Any questions so far? Everybody happy? Anybody too hot? Anybody too cold? I can't do anything about it. We're in a hotel or in a convention center, but just like to check. We're doing okay. All right. Ron, you're up next. So Ron, the next Ron. In the council, we have 5 Rons, which is always a new. Yeah, it's a requirement to have at least 5 Rons on the council at any one time.
Always looking for more.
Yeah, so if you're a Ron, we have one Aaron, and we call him a Ron in training, so he's a Ron. You got one. All right, you're all set.
Now, let's see if I can see this without my glasses. Nah, I'm going to leave these on. Okay. So I was already introduced. My name is Ron Ambrosio. I've been on the council since it was formed, and was involved in the formation of it back in 2004. So I like to refer to myself as the Silverback. I'm going to talk a little bit about some of the challenges of designing for how we get to the future energy system that we're all looking for. Talk a little bit about what that future is, talk about the kinds of tools that we can apply in order to help manage and design for that future. So the first thing I'll touch on is a project that the council has been working on for about a year and a half, called the Future States Assessment Project. That is going to be published in the very near future. It's going through final editing and approvals.
It'll be out this week. We'll announce it at the symposium.
Out this week. Going to announce it at the symposium later this week. So the Future Vision States Assessment is a piece of work that we looked at about 10 different organizations. They're listed on the right side. You'll be able to see these slides at some point. They'll be published on the council's website. So I know not many people except those sitting close to the screens can read these things. So I'll quickly mention them. The Commonwealth Scientific and Industrial Research Organization down in Australia, they have a Future Grid Forum, and they've developed future requirements, future vision. The Department of Energy, the Electric Power Research Institute, the GridWise Alliance Industry Consortium, and just a quick aside, the GridWise Architecture Council and the GridWise Alliance are 2 separate things. They happen to use the same name because that name was trademarked on behalf of DOE about 20 years ago. There was a GridWise program in the Office of Electricity at the same time. So the GridWise Alliance Industry Consortium was formed around 2003. I was involved in creating that. The GridWise Architecture Council was created in 2004, a year later, but they're 2 separate organizations. Also the IEEE, the Independent Electricity System Operators, IESO, National Institute of Standards and Technology, NIST, the Pacific Energy Institute, which is a utility industry think tank, and the Utility Technology Council, the UTC. The objectives of this assessment project was to identify for each of these stakeholder visions what were the similarities, what were the differences, what kind of divergence is there, and what did they each think about the impact on their stakeholders. And then draw from these visions what are the architectural challenges that emerged out of these 10 different points of view. So, quick summary. Again, the report's coming out this week, as Jamie said. Similarities, everybody agreed that the grid is going to have to go through significant changes, and that the future grid needs to be efficient, affordable, and economic. In terms of differences, they differed primarily in 2 areas. One had to do with the stakeholder involvement. What did each of these groups consider the key stakeholders? Some of them said all parties that are involved in the use of electricity, the supply of electricity, the delivery of electricity, the operation of markets, et cetera. And some others were really focused on the customer end and prosumers and things like that. The other place that they differed was in terms of cleaner energy and environmental protection. About half of these organizations called that out as a key issue, and the others didn't. To summarize the architectural challenges that came out of this piece of work, developing new industry structures, and that means not only physical grid structures, but also business model structures, regulatory model structures, et cetera. Transitioning from a very centralized power delivery model to one that's highly distributed. Transitioning from silos to platforms. And that's not just in terms of technology, vertical implementation silos, but also business silos within industries, within businesses, versus a more distributed platform kind of model, a more flexible model, and a lot more information sharing between the different parts of the business, between the different parts of the grid. Developing effective data communication and enabling control and coordination of distributed resources across the grid. Standardizing interfaces between different technology sections of the grid and between different businesses, and developing structures that can accommodate large quantities of distributed energy resources, DER. One of the things that the council is trying to sort of bring to the attention of the industry at large at this point is what we're referring to as the need for a back from the future view of how to get where we're going. Bridging the gap between today's grid and these future visions that we were just talking about. Again, it's an eye chart, but you see three major layers here moving from left to right in time. Where we are today, this is referring to, there's significant variable renewable energy and distributed PV, but there's still a lot of bulk generation, a lot of what's referred to as synchronous generation feeding into the grid and supplying the loads for customers. Where we're moving into now, moving through, the next layer up is a higher variable renewable energy and distributed PV penetration and more decentralization. Where we want to get to is very high penetration of distributed resources, batteries, rooftop solar, large-scale solar farms, et cetera. The problem is, if we look at today's grid and just take a traditional incremental forward step kind of change approach, some point we're going to hit constraints in the fundamental design of the grid today. There'll be inherent power system limitations on how much distributed resource can we integrate and manage. And so we're going to have to make some more significant changes in the design. Now, that's where the challenge comes in. If we don't do this carefully, those step changes are going to cost a lot of money. If we wait too long and then realize we've hit a boundary, we've hit a brick wall, and we have to change some things significantly, that's going to be very expensive. That's going to be measured in trillions of dollars. If instead we take an approach where we're not only going incrementally forward, but we're looking at that end vision and saying, okay, let's work backwards. You know, if we were there, how did we get there? Do a sort of bridge from the future back kind of design exercise and see how do we make these two lines come as close as possible, minimize that step function, and minimize what could be trillions of dollars of investment. You know, we're talking a lot of money. So from a pictorial point of view, we're really talking about, and this is the Sydney Harbor Bridge. One of our GridWise Architecture Council associate members, Mark Patterson, has sort of formed this concept. And so a lot of the graphics he has tend to come from Australia. Grid architecture tools and grid architecture methodologies and approaches are a key method for how do we deal with the design and the implementation of the grid and how we have to change it. And we can use these tools to both look from today's system, deterministic, centralized, and fossil fuel-based, to where we want to get to with highly flexible, hybrid, net zero, highly distributed kind of grid design. So we're able to take a present forward approach and at the same time, in parallel, be looking at how do we work backwards from where we want to be? Because that can affect choices we make along the way going forward. Our incremental forward steps on grid change, grid evolution, can be informed, and maybe instead of making this choice, you make this choice, and in the end, we minimize that step function, that gap in the middle of that previous chart, and therefore we hopefully minimize the investment to some extent and make for a better design, not Band-Aid patched design to get where we're going. You can look at it another way. Lower left is where we are, upper right is where we're going. How do we look backwards, decade by decade, on how we could get to that green destination from today's blue state of affairs? One of the challenges in decarbonizing power systems is that as we add more distributed resources, as we add more information, as the calculations to optimize decisions become more complex, things can tend to become more volatile. But the grid still needs to balance every microsecond of the day of the year, the supply and demand. Okay, this just, as one of our former council members used to say, there's still the pesky physics involved of the day-to-day operation of the grid. Okay, so it's a very challenging real-time supply chain industry that we're in. The supply of electrons in real time, almost instantaneous. So the power system that is starting to emerge is one that requires a completely new level of dynamic whole system interdependence. We can't silo bulk generation and high voltage transmission and medium and low voltage distribution and customer resources can't be viewed as independent of each other. They have to be part of a whole system optimization, because we'll get to the point where the left side here, bulk supply, could be serving close to 0% of demand at any instant in time to 100%. And at the other end of the spectrum, distributed resources and batteries and things like that might at times be providing 100% coverage of the demand, Or there could be other times when it's nighttime and there's no wind and the batteries have depleted and you've got zero supply and you're dependent on the traditional bulk supply. So that sort of integrated view is where we have to get to, both conceptually and physically and operationally. So, grid architecture, which Dave Forfia will go into a little more detail on later, and you'll see a couple of the same slides. I'm really bringing it up to say this is a tool that's very important to achieve what we were just talking about. The grid is viewed as a network of highly interconnected structures. And planning for distributed energy resource integration has to account for multiple grid structures at the same time. Structure sets the essential limits on what a complex system like the electric grid can and can't do. So the diagram on the right is showing different aspects of this multi-structure model. Electrical infrastructure, so the circuit topologies, generation structure, load composition, industry structure, operations, planning, electricity markets, regulatory structure at all levels, from federal to state to local, digital infrastructure, information, networking, processing, persistence, control structure, protection, electrical protection, control synchronization, things like that. And then convergent networks. What other networked structure is there that we have to worry about interacting with? Ron was just talking about transportation. As that becomes more electrified, that's one. Fuels, the fuel supply infrastructure. So there are a number of other large-scale structures that the grid both depends on and interacts with. A very high-level, quick description, and again, Dave will go into this in a little more detail, of grid architecture. It's an abstract depiction of a system consisting of black boxes that are demarking major sections, major functions. Component structure, market visibility, external visibility. Grid architecture is the highest level, most abstract representation of the grid with ultra-large scale complexity. And so it enables the practitioners to reason about the properties of the grid, the behavior, the performance, the economics. So this is not just about the physical electronics. It's also, as I said earlier, about the business models, the policy and regulatory models, et cetera. So market structure influences the system architecture, the information networks, the theory of networks, and the control engineering, the real-time, literal control of the equipment on the grid. They all combine to define grid architecture. And there's some very good information on the PNNL website at that URL below. So critical issues that grid architecture can identify: tier or layer bypassing. So I think the simplest example I can give you of that is, there are some market operators on the grid. So they're kind of operating mainly at the transmission and scheduling of generation and delivery to distribution systems, but they're also looking at influencing customer distributed resources, demand response, things like that. That's an example of tier or layer bypassing, because the distribution company that's responsible for moving those electrons may not have any idea what is its customers are being told or their equipment is being told to do by a layer above them. And so they can't really manage correctly what's going to change in terms of the load on their distribution grid. So you don't want to see that happening. Coordination gapping, hidden coupling. Are there hidden links in terms of you change something here and something over there suddenly changes and you didn't realize that there's a cause and effect relationship there. So grid architecture helps identify and expose those. Latency cascading. If you have too many layers that take a little bit of time and you've got a bunch of steps, you may build up too much delay to have a real-time reaction. So you have to think about what sort of latency buildup do we have? Do you have too much time spent computing an optimized result? You know, a time wall in terms of computational efficiency. Cybersecurity structural vulnerabilities, and back-end integration constraints, the back-end being the business of the grid, for example. One other piece of work that the council did probably 15 years ago now, one of our earliest pieces of work called the GridWise interoperability framework. And this has been used a lot in industry, a lot in the standards bodies, not just in the US, but worldwide. It's really where we took a look at the grid. And for those of you, I didn't see many hands in terms of people with an information technology background, but if there are a couple in the room, you may have heard of the OSI model, layered model of information technology networks. We sort of took that and expanded on it. The lowest levels of what we lovingly refer to as the GWAC stack are up here. They have to do with the sort of technical or syntactic connections in the grid. What are the mechanisms to establish physical and information connections between systems within the grid? Network interoperability is the next layer. Yeah, the mechanism to actually exchange messages between systems across a variety of networks. Then syntactic interoperability, being able to understand the data structure in the messages that are being exchanged. A lot of this comes up in the control systems portion of the grid, but it also is key to the business models. The next layer is informational or semantic. Understanding, not just being able to parse, but actually understand the content of the message data flowing around in the grid. And then business context, awareness of the business knowledge related to a specific interaction. Might be a business transaction, might be something between across the meter boundary where a customer's demand response resource, battery for example, is being asked to have some sort of response to a signal from the grid. And then the highest level, and this is really where we went well beyond the OSI model, is organizational. Business procedures, is there alignment between operational business processes across the grid, across the players in the grid? Business objectives, strategic and tactical objectives that are shared between businesses that make up the utility system. And finally, economic and regulatory, political and economic objectives as embodied in both policy at the state and at federal level, and maybe at the municipal level, as well as then regulation that embodies that policy and enforces that policy. There are also a number of cross-cutting issues that we identified. So things like security and privacy cut across all these layers. There are about 12 of them, 11 of them here. What's the relevance to grid architecture? Well, the GWAC stack provides a framework for identifying system qualities and properties of the grid at all levels that I just showed on that previous chart. Technical, informational, and organizational. It defines key points of interaction, interoperability, and integration. Interoperability is something that the utility industry started focusing on heavily about 20 years ago now. And a lot of that came out of the GridWise Architecture Council identifying that as a crucial obstruction to being able to move to a future energy system. So interoperability is well established. Standards activities are well established now. It allows experts to work within their domain, but still be able to understand how they impact other parts of the system. It sort of brings that out very simply and visually. And then another piece of work that was done by the National Institute of Standards and Technology, the Smart Grid conceptual model, when you combine that with the GWAC stack, they really provide a consistent approach for design validation. And that's a key objective in grid architecture and how we get from today to the future. That's it for my section. Let me see if there's any quick question or two. I'll repeat the question. Oh.
I'm having trouble understanding whether or not who you invited to ask the questions. I want to mess up the flow. Having been an advocate on behalf of good utility policy for 4 years in New Orleans, I don't see anybody in the role as a regulator who can bring this idea that you're talking about.
Which is why we're here. When we started with the issue of interoperability, your comment was valid about interoperability 20 years ago. So a big part of what GWAC does is try to identify key future challenges for the industry to keep moving forward and engage all of the parties, not just the utilities, not just the equipment providers, not just the regulators and the policymakers, but all of them. I've always described this as sort of a three-legged stool. We can't evolve the grid without evolving both the technology, the business models, and the policy and regulatory issues. So we're at another inflection point right now. The three that the council has dealt with, first was interoperability. We sort of got that well established, moving on its own. We then moved on to transactive energy. And then a couple of years ago, we decided there's another inflection point. Transactive energy is more well understood by a lot of practitioners now, and we identified this next issue. So this is the education process. So you're absolutely right. The regulators aren't going to know what this is yet. We're starting to engage with them.
Decision makers checklists?
Yeah, one of the artifacts that we developed in each of these inflection points were, in addition to the key documents like the GWAC stack document, the interoperability framework, we also going to develop decision makers checklists that are aimed at, in particular, policy and regulatory and executives, so that they can start to understand what we're talking about and start to react to those issues when they're brought to the table.
I have a follow-on comment. I don't know if any of you is compatible.
A little closer.
A follow-on comment. I don't have the idea whether this is really constructive, but I'm trying to be constructive. So when I was a graduate student at Berkeley, my thesis advisor created a model of evolution. And evolution is a process where they're almost completely ignorant. The thing that's evolving, the genome, is almost completely ignorant of the biosphere. and just accidentally makes good choices, although more often it makes deadly choices, which those things drive it. And I think that's how the grid of the future will evolve. If your clever ideas never get into the heads of the people who make the decisions.
In response to what you're saying, I think part of what we're hoping to do, and we've been successful during these last two inflection points, we're hoping, so the genomes, that don't react well and die off, that's the excess cost in that middle that I said we've got a step function that could be trillions of dollars. We've got to try and minimize that. We've got to try and figure out a way to provide some guidance so that the genomes evolve in a slightly more informed way, as opposed to having too many subspecies die off just randomly. We're hoping it's not totally random. We can't solve the problem perfectly, but we hopefully can provide guidance that makes the decisions converge a little bit better than they might have if just left totally random.
I'll add to that, Aaron. So, I believe in evolution, but sometimes we have to get evolution guardrails. The attempt is for us to get a guardrail. Because the bottom line is, and this is what I'm going to talk about, is they don't have time to wait. They don't plan to sit. All right? So we need your help as well. So I was going to start saying we need to pump up the energy here. All right, so I'm Cake, and I run a company called Dynamic Grid, and I love these hand mics because then I can walk around. But doesn't that go into the recording? Goes into here directly. Oh, geez. They just put a straight jacket into me. I can't just stand here. That's impossible. All right, so I'm Kagan. I'm CEO currently, though I'm trying to transition to Chief Product Officer of a company called Dynamic Grid. We provide systems architecture support, complex systems research, as well as controllers for the utility industry and microgrid industry. So please don't leave. I'm going to talk about you, right? And it's the 3D, though there's actually a fourth one, and sometimes people have 5. So I'll kind of touch on that a little bit. But the 3D principles of grid services is how can you provide services to the grid to make the grid work better? And then who are the stakeholders in the grid, and how are they, what are their roles, and how do those roles intersect? So I think both Rons, we do have definitely too many Rons.
No.
Never too many Rons? Okay. So we're in a period of disruptive change in the electric grid. And the scale is really, really accelerating. When we started out in Pearl Street, New York City with Edison, we had a microgrid. We literally had a microgrid. And basically we had microgrids for 20 or 30 years. They slowly coalesced by 1920. And then we had the rural electrification pathway. We started getting power to the people out in the farms, out all the way out. And that happened 30s to the 50s. And then we went from a basically stable time. Load growth is, as Ron B talked about, we had a lot of load growth in the 50s and 60s with industrialization. And then in 1970, we started building regional grids, the ISOs. And we talk about the regional transmission authorities and the independent system authorities, organizations. And we started building regional grids. And now we're starting to come full circle and come back to microgrids. We're talking about people-centered power. So I'm going to talk a little bit about that. But the bottom line is the pace of change is accelerating. In the next 25 years, we're going to see the fastest change in our electric grid that we've ever seen, right? Quicker than in the 20s, quicker than in the 70s, quicker than ever. And we have to do this because we need to get to decarbonization. And that seismic shift is actually occurring by the people at the bottom of the system. We're moving from this centralized power supply system to a grid architecture where you, the consumer, and we're all consumers, we're part of the industry, but we're still all consumers, and we're critical to the solution. You often hear about the term prosumers. Well, consumers are now turning to prosumers. We are putting solar on our buildings. We are putting storage in our buildings. We are going to be able to both consume power and provide power at all times. Ron A. talked about, one side of the system is going to be producing all power at one time, and then another part of the time is going to be producing nothing. And the other side, the mirror image. And we're going to have to manage all of that in real time. That is where we are going, where Ron B. talked about. This is the future state. And we have to figure out how to manage that. And that's what grid architecture is about. So this actually comes from IRENA, International Renewable Energy, I don't know. It's a world body. The power system of yesterday was centralized. Large nuclear power plants, coal plants, hydroelectric plants, producing gigawatts of power, working way through transmission to a local distribution line down the street. And it was easy. It was easy to conceive of. Architecturally, it was really, really simple. One-way power flow. Homes just consume power. Very easy. Turn the light switched on, consume power, and literally the frequency changed in your coal-fired plant a little bit to handle your power. And there was almost no renewables. We didn't have solar. When I started in this industry a long time ago, we were in the death throes of the solar valley of death in the 80s. And there was almost no renewables. We couldn't afford it. But today we can. And the emerging scenario is distributed energy resources on the transmission system, on the distribution system, and on our homes. We're going to have local battery storage. We're going to have both smart homes and what we talk about and what the GWAC has talked about for a long time is smart grids. How do we make the grid smarter so it manages the system better? The bottom line is the structure is changing. And we're talking about grid architecture. We're talking about structure. How is the system structured? But as I circle back now, customer needs are the center of this new grid paradigm. Customers want reliable power. They want resilient power. They want cheap power. They want it all. So how do we give it to them all? What they're really looking for is a customer-centric grid. It was always the utility-centric grid. And now we're looking at a customer-centric grid. It's going to end up being decentralized, power at the edge, distributed across both centralized systems as well as down at the end. It's going to be democratized. It's going to be people-centered. It's your grid. It's not the utilities grid. It's not your policy maker's grid. It's not your legislator's grid. It's your grid. And it's going to be decarbonized. That is really the key, because we're setting a plan right now. So this is back to that same slide, the 3Ds. And again, I say decentralized, distributed, democratized, so we can decarbonize. We're going to have distributed. We're going to be resources everywhere. It's going to be decentralized. Decentralized meaning the control is going to be throughout the entire system. It's not going to be some grand system optimization. My research work is mostly in complex system science. And we can't do a system optimization across the entire grid. We need to find methods, computational methods, that allow multiple areas of control and coordination to work with each other in a streamlined way. We will never do a system optimization. And we want it democratized. We want the power, I sound like a power with the people. It's going to be consumer-centric. Consumers, because they're prosumers, are going to be at the center of the system. So we're talking about grid services. How do they become the center of it? This emerging scenario of grid services, where you have distributed resources, I am both going to be consuming power, and I'm also going to be providing power for my solar equipment or my wind or my battery. Our buildings are going to become digitized. In order to do that, in order to manage supply and demand, I can't remember which one of you two talked about, this is a real-time system. Not as real-time as it used to be, because we have storage, and we're going to put more storage, but basically real-time system. You have to balance the system. The electrons, even though they don't actually move, they only oscillate physically. A lot of people don't know this. We have to balance that oscillation in real time. And we need to make it smart. And being decentralized coordination. I made the slide and I forgot what I was going to say about that. Decentralized coordination is an enabler. The idea of having decentralized control, being able to talk to each other, the interoperability we talked about, being able to understand what Ron A. talked about is the semantic understanding, is understanding what the goals are on both sides of the transaction, and being able to make this, in effect, ecology of the grid. And those services, that ability to have a smart building, a smart community solar, a smart distribution system that can provide grid services both downward and upward is very, very important. So this is the 3D grid. Thank you, Myron. The 3D grid, the demand side is critical. The prosumer side is critical. So another eye chart, sorry. There are, and I'm going to start with the right side of this, it's operational grid services. So the distribution grid is going to become more and more peaky, more and more variable. You're going to see large peaks at NREL, if there's any NREL people here. NREL did a study a few years ago where we're going to see by 2050 81% more demand than we do today. And I think it was a 2020 study. And Jamie goes and wipes his head like I'm lying or something. And we're going to see 2 to 3 times more peaks. So we're going to see these unmanaged now transportation loads immediately peaking at 5 p.m. when everybody comes home. Well, how do we manage that? So we're talking about peak load shading. We're talking about supporting the voltage in the system with batteries, things like that. Frequency regulation. We've had batteries and frequency regulation for a while now, providing very fast response to keep the 60 hertz cycle intact. We want to do some work that Lawrence Berkeley Lab is working on is, I got to give a shout out to LBL, come on. I work with them too much. Where's Bruce Norton? Is he here? We got to do load shaping. We've got to cut down those peaks and shape when we use power. And then I'm going to skip over emergency power and no spin reserve and stuff like that because I really don't understand that stuff. But that's okay. Those things support the grid so that the lights stay on. And those are going to be valued, need to be valued by the grid so that you will do them. So you will do this stuff. As far as the customer is concerned, we're looking at how do you make money doing that? How do you want to put those assets in and make it worth something? I was in a workshop earlier today when we were talking about the interconnection process and talking about, how do we value these assets on the grid so that more of them come? And that is going to be, how do we make self-consumption of PV worth it? How do we control demand and save money on demand charges? How do we do time-shifted charging? How do we do time of use optimization? Or my favorite is dynamic pricing. A lot of people probably don't like that idea, but I'm a dynamic pricing person. And how do we energy arbitrage? How do we buy energy cheap and sell it from our battery when it's high? Those are all the grid services that I think Jamie will talk about later that we have to enable in a grid architecture that we create. The bottom line is we provide grid value to these resources. We enable grid democratization. We allow all of us to participate in the grid and not only make money, but make the grid better. I'm sorry, I'm sounding like a televangelist now. Sorry, I apologize. So who are the stakeholders? Well, I think we raised hands before. There are no regulators or legislators here. Sorry. We're safe. I wrote a little bit of legislation. So regulators are very important in this. They set policy. They set policy for public utility commissions. They set local policy. They can either completely stop this in their tracks, or they can enable it, or they can make it worse. We need to work with them to make it better. Develop regulatory approaches that significantly support consumers. Develop approaches that provide parties access to value in the system, not just the utility, but everyone, the consumer and the utility and communities. And they need to implement best practices and improve value for all parties. Utilities have to be part of this game too. They have to implement platforms for connecting customers, the regional ISO, and their partners. And support a value-based approach where they value what we can provide to the grid to solve their problems. And I'll stop there with the utilities. I can't beat on utilities too much. I work with them too much. Technology providers like myself need to partner with customers. We talk about VPPs, we talk about DERM systems, we talk about storage providers. We have to partner and see them not just as a customer who's going to give me some money, but as a partner in making this change. We also have to resist the trap of just incrementally improving the technology a little bit at a time. We have to have this future back idea of seeing where we want to get to and figure out what the paths are. And it's not going to be just one path. We're going to have to make some twists and turns as we get there. But we're going to have to really think about the future now before we end up, I like to say, getting into box canyons and end up spending, Ron Ambrosio has talked about, spending a pile of excess money. We don't want to do that. And then consumers, all of us. We need to engage with utilities and legislators and technology providers. Help them provide services. Advocate for providing services. And deploy systems locally. The IRA has been a phenomenal value stream for getting money into the system. We need to keep the momentum going. That will make our system democratized. So what are some of the challenges in regulation policy? Regulators are nervous Nellies. Since there's no regulators, I can say that. They're scared of change. And it's our job to show them that change is not scary, but can be managed. There's going to be new requirements on the grid. There's going to be new technology. There's going to be new business models that are going to challenge how they regulated in the past. But we acknowledge that past regulation isn't quick enough. The transformation is accelerating. We're not going to get there. And this is a part of what we talk about in grid architecture. There's a group of us in the Grid Architecture Council who really talk about this future back and how fast the transformation is happening and how we have to have more consumer-centric. On Wednesday and Thursday, there will be a gentleman named Lorenzo Christoph, who's a member, who really talks about distribution system operators and the idea of having community-based power systems. Those are going to be harder to manage, but we can do that when we use grid architecture. And regulators really need to embrace new innovative regulatory structures so we can manage this increased complexity. If we do what we've always done, we will not get there. So what are the challenges in utilities practice? And basically utilities, and I do say this to some utility executives that I know, they're still dinosaurs. There's going to be new system requirements. They can't, again, just like regulators, rely on the past. There's some really good utility presidents. One of them is a former NREL, Brian Hannigan, who's a friend of mine at Holy Cross Energy. He's out there trying things. He's not afraid to break it because he knows he can fix it right away. We need more of those type of utility executives. It's lucky he's in a small utility, co-op type utility. So the utility business as usual is insufficient in this transformation. They need to embrace a value-based approach to the grid services. The ability to, thank you, Myron, my mentor here, minder, I should say. And they need to develop and embrace new structures, working with regulatory people, working with customer groups, communities, to manage the platforms that will allow us to manage the common complexity. It's already complex. We don't need it more complex. And opportunities for people like myself as technology providers is to not rely on what we were doing. Again, a lot of this is don't rely on the past to inform the future. Think about the future to inform the present. There are going to be new business opportunities, and we need to support those to transition. So small, tight things. Resist incrementally building on technology of the past and build for the future. Develop platforms that supports today's system and supports tomorrow's complexity. And most importantly, partner with consumers. See them as a part of how you're going to provide your solution, not just a value stream for you. See them as partners. That will increase your quality as a technology provider, lower cost, and provide more value to the consumer. So, bottom line, as I'll say, consumers are the linchpin. It all comes back to the consumer. The regulatory, legislators, the utility, the technology providers, comes back to the consumer as the linchpin in the future grid. We're going to have a new decentralized and distributed system, consumers at the center, that will create increased system value in the distribution grid or in the entire grid, which will allow us to make a democratized system, which will then allow us to enable decarbonization. As consumers, now I'm on my soapbox, engage with the system to create new value for yourself and your community. Community-based solutions. Deploy those systems in your community and on your buildings to support that value and deliver and work on delivering services to the utilities, working with the utilities so that there's this interchange of value. And that's all I have. Questions?
Well, I'm sorry, I'm going to ask a question. You guys may ask questions too. I'm really paying attention. I think the 25-year period to me is emphatic. I live in New Orleans. It's going to be smothered by sea level rise. We have to get decarbonization ASAP. That's where the deadline is. All this building out that's going to happen in the future, that's nice. That's not going to save my home. That's where the deadline is. I think that's the important. The other thing I wanted to add on, which is kind of slightly contradictory, and that is that I think the multi-trillion dollars that was spent by Biden, which I appreciate, is approach to try to solve the energy problem, could have all been funded by a good energy policy with the regulators. I mean, we've gotten all the wasted money that's going through the utilities and not to the benefit of the consumer or the utility, in turn into our rates. We could have taken trillions of dollars out of our utilities anyway and paid for the same stuff without that. And when we have subsidized energy policy versus performance-based energy policy, and we get stupid things done. It's happened over and over again for 4 years.
So Myron is speaking on Wednesday, so we'll talk about that.
Thank you so much, Kay. I agree with everything you said. I do have a question about the consumer. So one of the things, I'm curious how you're defining consumer. So I think for at least what I see is that, and I'm more shocking than what you know, that consumers actually don't really care. Not let me just care. They care, but they don't want to do anything. So I think that what is going to be necessary is automation of the consumer edge to enable, to integrate with everything. So I was curious, when you were talking to consumers, how are you defining it and what were you thinking would be the activity? Because I think the actual consumer, whether it's commercial or C&I or consumer, they're not going to really want to be looking at their app or doing anything like that. It has to be automated.
Yeah, perfect point. I mean, the bottom line, I run an AI company. So it's hidden purposes. I run an AI company. So our energy management systems are all AI powered. Set it and forget it. That's the only way it's ever going to work. And I think I'm getting the hook.
Oh, that's okay. Mr. A, there we go. Okay. I just want to make sure everybody has a chance for questions along the way. It's fine. We were going to take a break now, but I'm kind of getting the idea that you guys are all taking breaks as needed. many folks need a break? Good, I see two. Go take a break. We're going to continue. If 40 people said we all need a break, I think some people would like to get to the after party. I don't know where the after party is tonight, but let's bring up, I think David wrote next. So let's bring up David, and we'll try and get about 40 people. So, we folks finding this valuable so far? Okay. This feedback for us too. We're all volunteers. We are not professional speakers. We are not professional PowerPoint people. We are technologists and people who deal with high-level concepts. So we're trying to break it down for you here. So just let us know what we're doing. Okay. Thanks, David. You're up next.
Hi, I'm David Forfia. I'm a consultant with Utilicast. In a former life, I started my career at Austin Energy, which means I rode in bucket trucks. I climbed inside of boilers, been in switch yards, I took trouble calls. If you start out in IT at Austin Energy, they also make you learn how to climb poles, just for the sheer fun of watching the 25-year-old CIO climb up a pole and hang on and not catch the footballs when they throw it at you. So the two things I'm going to cover today are roughly 22 hours worth of material. My goal is to get through it in roughly 20-25 minutes high end. So the two things we're going to cover, grid architecture in a little more detail than you've heard sort of to date. Second thing I'm going to cover, transactive energy, as we go through and sort of what the concepts are and how it sort of applies and can apply as part of implementing a grid architecture.
Stay close to the left.
I'm watching the mic. So here's the high-level view. Ron A. Went through and did it. The couple key points I want to cover on this slide. Number one, the person who sort of was the godfather of grid architecture, Jeff Taft, has a PhD in control systems. Right? PhD in control systems. I, unfortunately, am a mere mortal. So I do not have a PhD in control systems. I'm really good at implementing systems. If you tie in the theory of network and doing system architecture and apply it to the grid, you end up with grid architecture. And there's a lot of materials on the P&L site. I'm going to cover some of them during this presentation so you understand how the techniques and the deliverables of grid architecture can help with setting policy and looking out in horizons in the 20-25 year perspectives. So what is the core problem of grid architecture? Make sure that we don't end up with stupid investments, as Myron said, right? Limit the propagation of undesired change effects, right? There's going to be constraints. We have to go through and address them. We want to, for the things we want to emphasize those. So as you go through and start looking at the characteristics, the components, and the structures, the whole idea of grid architecture is to get those things to where we minimize the bad, we emphasize the good, and ultimately you get into simplicity as opposed to where we are now. So my favorite slide from Dr. Jeff Taft's class. What's a low complexity system? The little egg timer, right? A high complexity system, the space shuttle. Okay, again, I'm a mere mortal. I would consider the space shuttle well beyond what I can do. But when you start talking about the world's largest synchronous machine, right? When you start talking about the electric grid, that's ultra large scale. So stuff breaks all the time. Failures are normal. You have competing goals of an ultra large scale system. You want to be both affordable and reliable, right? So no, you can't have 9 of everything to never have the power go out. Sorry, Ron, I have a backup generator, right? So you end up with those. As you start looking at the requirements and trying to balance these things out, the techniques that are part of the grid architecture practice help communicate those in a way that people can understand. Because we're dealing with something that is so complex that, you know, once you get above like 20 things, I got to start drawing pictures before I can process it. When I'm trying to figure out how you interrelate, you know, 3 interconnections, and, you know, I grew up in Texas, so sorry, it's a whole other country. As you go through it, how do you deal with that level of complexity? Because complexity introduces challenges. However, if the grid is ultra large scale complexity, then what the heck is that? Right? So you now have one ultra large scale system that is interconnected to 6 others. Right? Dr. Taft called them convergent networks. I call them a whole lot of complexity. When you start tying petroleum and the communications infrastructure and financing, right, into what we're doing, water, right, it all ties together. Remember, I live in Texas, right? If you want to know how related electricity is to natural gas, have a freeze. Pump stations don't pump a lot of natural gas when they're off, right? So you start taking a look at all the interrelationships. That's the techniques and the practice and the deliverables of grid architecture. So there's our network of structures, right? Ron's already covered this, great graphic, right? The key thing that's at the heart of this diagram, everything else is more or less physical, right? Everyone can draw a grid diagram and how things are connected. You can take a look at regulatory structure. I'll show some examples of that. But in the middle, there's a lovely green box that talks about a coordination framework. The heck is a coordination framework? It's like when Dr. Taft did the architectural review of this at AHR Expo in 2017, a hand goes up. Hey, Jeff, what the heck? Well, that doesn't actually exist. That's really the focus of grid architecture. Tie these things together, make them work together, make them deliver the results that they need to, working as a network of structures. And that is kind of the heart as we start talking through what are the artifacts and the deliverables that come out of grid architecture. So I'm pragmatic. I get paid to implement things. I have since I was, writing code in high school for money. That's the classic side, right? Everything is well-defined. The grid is big circuits. People have seen system of systems diagrams where you tie your ERP system to your billing systems, to your customer systems. That doesn't work at the scale we're talking about. Everything is now much bigger. The problems are more complex. The way you go through and express them to different people has to be done differently. A lot of the work that P&L did with developing grid architecture was done in practice with part of the New York rep because it's a big problem as you go through this. So, big picture view, at the highest level, you start out with what you're trying to accomplish, right? Jeff called them system qualities. What do you want to achieve? The goals that Kay and Ron, if we could get another Ron and make it easier for me to go through this.
I changed my name next week.
There you go. The goal is to go through and figure out what the big things you want to achieve, right? Hey, we want to be sustainable. We want to be affordable. We want to be resilient. Those are high level goals. That's the domain of grid architecture, right? It's not a use case, right? It's not going through and saying, hey, I want to implement XYZ system, right? So what you're trying to do is figure out policy level, vision, what you want to accomplish. That's the left side of this domain, right? On the other side, for those of us who actually have to hook things together, you got to figure out what the system has to do. So the first one is, do the structures we have now work 25 years from now? Right? I make an argument that given where we're headed, we need new structures. The other part of that is components, right? I didn't use my favorite slide from Jess, which is the components are black boxes, which means things occur, but you can't have a miracle occur for those black boxes. You can't go through and say, hey, let's get Marty McFly, right, in the flux capacitor, give me a can of beer and a banana peel, and I'm going to power the United States, right? That's not part of grid architecture. But you can go through and say, hey, I need something that retains 72 hours of power that I can use when it's dark, right, or you have a big storm. I need some way to be able to sustain a lot of microgrids if things have been washed away by the latest hurricane or derecho or insert the new cool storm name coming from our National Weather Service. The corollary to this is what's coming from those of us who actually have to implement things. So our goal is to go through and provide the structures and components that meet those longer term goals. So when we start talking about the 3 or 5 Ds to be able to implement, that's what grid architecture focuses on, right? How to go through and get those things, how to go through and express them so that a diverse audience of experts can understand how they all play together. If you've ever watched a room full of specialists talk past each other, right? Ron started out with our calendar, right? Our meetings are public, please show up. So you can watch 13 people talk in different languages on every call. So as you go through and put these together, I'm old enough to remember what a vellum is, right? So for those of you who haven't dealt with blueprints, right, who've come up in the level of CAD, right, part of what you do within grid architecture is you provide different viewpoints. So in this case, I have 4 different viewpoints. They address certain things. The same way you get plumbing diagrams to hand to your plumbers and wiring diagrams to electricians, and why you have a civil engineer to make sure your house doesn't collapse. That's the part of grid architecture that gets something that takes it from theory into something that people can visualize. So any attorneys in the room? Okay, apologies. What we found out during the New York Rev, don't draw an attorney a picture. Please give them oodles and oodles and oodles of text to read as opposed to a diagram. Just the way it works. So at some point, as you put it together, you start getting more complex diagrams, right? It starts to show how everything's interconnected. The picture helps most people who didn't go to law school understand how things are doing. And at some point, if you go through and take a look at how all the players within a space and how the regulatory entities look, you start to get a framework that helps you achieve the goals that you're trying to get at, because it's much different than dealing with, hey, give me a new billing system or ensure that I don't trip all the relays, right? It's a different challenge. It's a different approach. So as you start taking a look at the goals of grid architecture, it kind of flips the world on its head. Right? The current state is an input into what you're doing. It is not the output, right? So you take a look at what your requirements, your constraints, the changes, your view of the future, the principles that you're trying to achieve, you take those as inputs, and they end up with the components that you have to have. Not sure what they are, I just need a battery that provides 72 to 168 hours of power in the event that it can't charge. I don't care if it's a lake. I don't care if it's a flux capacitor. The requirements are I have to sustain for a week without being able to get generation, right? Same thing with what you can see from a system, right? Don't care what made it go. Don't care what type of battery. Don't care that it's a lake or pumped hydro, right? And then at some point, do those things need different structures to be able to get through? And ultimately, I'll highlight the key output. If you can manage complexity, you manage risk. Risk has a cost. Risk sends your projects off into the ditch. Risk makes you do stupid investments as you try to mitigate it. So ultimately the goal of grid architecture, and the reason why you start to apply it at really big levels, is because you want to minimize the complexity, because that complexity is what adds risk to your implementations. So at the end of the day, there's a million viewpoints. I'm not going through every viewpoint. I've got a cool architecture tool that draws a bunch of this that I use at clients when they ask for it. But ultimately, the goal is to go through that process, get people who know a lot more about their domains than I ever possibly could to express their ideas, make sure we get them all to talk to each other, and at the end, we produce a ton of documentation, right? This example is really nice. Most of this came out of, again, the New York Rev as it went through. But that was sort of the techniques of grid architecture. All these materials and a lot of the training is up on the P&L site. I learned a ton from Dr. Taft and Dr. Melton and Dr. Powell, right, about how to do grid architecture. I am pragmatic. I am not a theorist. I am a hands-on guy, right? Let's make lights go. I'm the poor guy at the top of the pole getting a football bounced off his hard hat, right? So that's where I grew up. That's how I work. But again, if you want more information about grid architecture, please go to the P&L site. At the heart of what they're doing in Australia with what Mark Patterson is doing with a lot of the work is the foundational level for a lot of things that Australia is doing, because they're ahead of us on implementation of DER and PD. So any questions on grid architecture before I head off into transactive energy? So that was 18 hours of training material. Any questions? There's a reason why we're recording this. Go back and replay it if you're interested. And Myron, the one thing I will say, our friends at NIST did pay a lot of us to, well, now they asked for volunteers and paid to record it. So part of the NAWRC training includes some of this material too. So if the good video editor, which you'll see on the website, will look better than what I just presented. So transactive energy. So anybody hear of transactive energy? So I'm going, if you want to know who coined the phrase transactive energy at the Watson Energy Institute, Ron Ambrosia, right? Well, I was chief scientist there. So transactive is a word, right? He invented the word. So what is transactive energy to the GWAC geeks? Because much like recording a song and putting it out on the radio, we defined transactive energy and did a definition, but we put it out in the world, so everyone sort of has their own. So I'll go back to the kind of the high level, right? It's both economics and control to balance the grid using value. Notice I didn't say coin of the realm or money, dollars, right? Yen, right? Value as the key operational parameter. Because what you value is different than talking about cost or payment. Our shorter version is kind of the same thing. It fits back when Twitter sort of constrained you to 140 characters so we could tweet it out. I'll end with the last part that goes into that. Using a distributed, agent-based collaboration, right? I do not want to balance my electric supply at my house every 4 seconds. I don't want to look at my electric bill more than once a month, right? Maybe less than that if I'm on levelized billing, right? So if this is going to work and these techniques are going to be one of the tools we use within a good grid architecture at the distributed level, it has to be automated. But then again, this is not a new concept. So this goes back to homeostatic control. You can tell the age of the report based upon the fonts. I tried to explain to my son, who's 21, what a typewriter was, because he found the one I had from college up in the attic next to my compact luggable, showing my age. Homeostatic control sort of lays the foundation for both what became, locational marginal pricing and what is the foundation of transactive energy. So you can trace it back to the work of Schweppe at MIT, late 70s, early 80s. So things are changing. Why should you care about transactive energy? I made the case for grid architecture before this, right? So you've got a bunch of renewables coming, the grid starting to blur between what's transmission and generation. You've got a lot of people doing stuff at the edge, right? And in some areas, you're seeing localized transactive markets, Australia, right? So you've got the environmental pressures, and this slide comes from OATI. Thank you, Farouk. Customer expectations and sentiments are down at the bottom. right? So things move at the speed of the consumers at some level of this. So as we start talking about this, right, cost of DER, renewables have dropped exponentially. So cost is now achievable. The cost of traditional stuff is continuing to increase. And then technology is advancing pretty quickly. The challenge we have, especially within the utility sector, is some things move at the speed of the consumer, right? How fast can you switch out to a Nest thermostat, right? Go drop $200, Home Depot, plug it in, I'm up and going. I would like to install a 10 megawatt generator on the distribution system. How long does that take? All right, got to do a rate case, got to go through and do it, go through a couple commissions, got to do the local. Okay, 5 years, 6 years, high end, right? Build a new plant, new dam, transmission line. Things are moving at different scales. And the one that moves the fastest is what we can do as consumers, right? If I am not burdened with having to go through a regulatory process to make the investment, and I can make this thing to self-optimize for myself, I can move at the speed of my wallet. And that's the way things are changing at this point. So here's our original roadmap, right? Ron showed the next version. But you can see back in 2015, we assumed this was going to be relatively smooth, right? Wow, were we wrong, right? So we assumed that as DER proliferated, we could keep doing the incrementals, and off we went. But I stole this from the same place Mr. Ambrosio got his, Pacific Energy Institute, from Mark Patterson's paper that's posted out there. That gap in between those two layers is the biggest challenge we face in the industry, right? For those of you who've ever done an accounting system change, right, at your company, right? Think of the blue line is we've gotten as far as we could doing QuickBooks, right? But now we've gone from a 100-person company to a 10,000-person company. QuickBooks isn't going to cut it. What do? Go do an RFP, you figure out what you're going to do, you pick one of the bigger players, and things go backwards because, well, you traded all the problems you knew for the ones you didn't know when you did the new system, and then eventually you can make the leap going up. That is our challenge as an industry, and to get through the next couple phases we're looking at for energy transition, think about making the switch from Quicken to QuickBooks to Workday, right? It's a big change, and in each one of those switches, there's a bump as you go back, as you implement the new. So why is TE relevant? Current grid can't adapt fast enough, let's be honest. Speed of the consumer, speed of the regulator, two different orders of magnitude. At the littlest. And also, I don't know why Ron valued putting solar on his house for his choice, right? I just know he did, right, and was willing to invest in it. I don't know what drove him to make that choice. I don't know how. Transactive energy is kind of the same thing. I don't know what your goal was for wanting to participate in the market or sell power or be a prosumer or provide grid services. I just know you do. And that's sort of the magic of transactive energy, talking about value. I don't know what you value, I just know you chose to do it. And that we can put a price on. We talked about what I call the grand optimization. Can you run a central thing like we do in the wholesale electric power to dispatch the most economic generation every 4 seconds across the entire grid? No way. It's like an NVIDIA stock would go exponentially faster than what it was if we had to go through and try to do the grand optimization. And then as things get more dynamic, the techniques of transactive energy allow you, right, to make your own choices, to support your own values, and to interact with others to be able to meet them. So ultimately, I look at transactive energy as an interoperability mechanism, right? And I'll go through some of the use cases as we go through there. But the idea is, how do we go through and make things balance? And I'll talk through it using my favorite graphic, which started out on a napkin in a bar, like most great things from the GridWise Architecture Council. So we started out figuring out sort of what's the view as we looked at transactive energy. So the infographic now fits on the page. Obviously, we got help to draw a graphic that good. At the top, hey, we wanted to go through and say the consumer's empowered. Things are going to be more clean in the future, and a lot of that's going to happen to distribution. You can prioritize what's important to you. No one tells you what to do it, right? Because we've pushed it down to the consumer to make the choices. They value what they value. And then at some point, stuff breaks, right? There's ice in Texas. There's floods. There's derechos, right? Stuff happens. There's morons with chainsaws dropping trees next to my house, right? So it happens. So I'll talk about it kind of from three zones. So regional, traditional wholesale markets, multi-state, ultra-high voltage, right? You're talking different voltage levels, different scale for what you're doing here. The traditional grid. On the seam, you have industrial and consumers and producers. So more and more, this is starting to look like Bitcoin miners and cloud data centers, right? So I've built some data centers. For the size that fits within that space, you could take 5 of the ones that I've built, and it would be the beginning starting point of an Amazon data center, right? Or Facebook, right? They end up on the seam in between both local and transmission. So they start to play in both spaces. As you start stepping through that, my favorite thing is new energy service providers. So as you step down the voltage and get to more local markets, things that are in the domain of single state, right? You're not going to FERC, right? To be able to do this, it's usually with state regulators to go through and do the stuff at the local level. You've got new service providers to be able to provide these services. Lots of things they can do. There's lots of services you can do on the grid. We don't proclaim to know who's going to win in the space. We just know that new is going to happen. But a lot of that's going to cycle around distribution. So we don't know what a distribution utility looks like in the future, right? Your guess is as good as mine, right? But we said someone's going to have to operate the distribution grid as it goes forward. That's sort of the next level seam. And then it steps down into what's a microgrid. What about the smaller commercial and industrial producers? My data centers were less than 10 megawatts. Right? The Facebook guys laugh at me. I tell them, oh, I built a 10 meg data center. Go away. The next step down gets you into where the world changes outside the speed of state regulators. So as long as you can meet the building codes, Ron's a building guy, right? He knows all about permitting, right? And standards to make it go. Once you start to step down to that level, things are moving a lot faster. And that's sort of the heart of transactive energy, because when you get down there, people are producing, and at the simplest level, the value of transactive energy, saying its value, if I was Ron's neighbor, right, when he had his power outage, and I needed to run a fan, I would bring an extension cord over, I would plug it into one of the ports on Ron's generator, and I'd hand him a beer. So, ta-da, I arranged transport, he provided the energy, and I gave him something of value that he would need. Transactive, right? Nowhere did I say I had to exchange money, right, as it moves forward. So ultimately, we end up in the make, move, use profiles from IEEE. So at some point, you got to make the electricity, right? It comes from someplace. Consumers become prosumers, right? I could connect to Ron's generator, I could connect to my solar panels, I could have fans, I could have Mr. Fusion, right? Something provides the energy. Transmission and distribution are different ways of moving, right? It's just at different voltages. And at some point, our regulators and the administrators that are the advocates for us in the whole, because a lot of this has to be and lends itself towards a natural monopoly within this space, especially on transmission and distribution. How many wires do you want? Right? Kay talked about the 1920s. Go find a picture of a utility pole in 1920s and count wires. All right. So the layout for transactive energy allows everyone to interchange within each one of those levels. And then I'm going to close with a couple things. There's Ron Slot, right? Energy Services Interface, which is at the heart of this. Ask yourself, do you know your doors are locked? I do. I have a quick set locks. ecobee knows I'm not sitting at my desk right now, and I'm here, right? So the air conditioning in my office is, at my house, is that vent's closed, right? It's going automatically, right? All of it's going through my Wi-Fi network, right? We complain about our cable providers, but you know, it's all going at this point. That's the heart of every building. As we start to transition, there are 125 million buildings in the United States. There are 25,000 generators connected to the wholesale, to the bulk electric system. So when we start talking about how to go through and interoperate this stuff, we're talking about 5 orders of magnitude more things to manage as we move forward. And that at the heart of itself gets into transactive energy. If we let the people and the buildings make their own choices, using the techniques of transactive energy to make the best deal to support their values, transactive energy is one tool we can use to get to our future. So my closing stuff, because I always get this, everyone starts to tell me what transactive energy is. So remember, we're the Architecture Council. We define its characteristics. We don't tell you what it is. So TE is only peer-to-peer. Not true, right? You can do a lot of things within transactive energy that doesn't need to be a peer-to-peer, right? Mr. Bernstein does not need a beer to let me connect to his generator. Well, maybe in that use case it would. But generally when you go through, hey, you know, if I'm going to go through and do peer-to-peer, there's lots of ways to do this. Right? Go look at the use cases for virtual power plants and exchanges within Australia, but you don't have to do it peer-to-peer. Okay, next one. TE is run and administered by a central authority. Right? You have to have one central throat that has it all, and everyone must tie to that. Again, not true. How many places can you buy stuff? You don't have to exchange the same way. Settlements and those type techniques, we'd have to go through and figure out how to do it, especially when you start talking about grid architecture concepts like tier bypass, think for 2222. Go through and say, which market am I participating in? Right. My favorite one, TE is blockchain. Well, that's cool, right? I want to talk, you know, proof of work, proof of authority, right? I can geek out on blockchain. TE can be administered on blockchain. There's some advantages to doing it. I don't have to, right? It's just one way to implement TE. And then last one, it's an energy-only market, right? Power only. No, right? You can do other things to exchange things of value. Voltage control, access to the transformers to figure out which EV can charge if you're overloading it, right? Scheduling. There's lots of things from a service perspective that transactive energy can help enable. It is a technique. It is a tool. It's one more arrow in the quiver of a regulator to help establish a good, sound sustainable approach to running an electric system. So with that, how do I do for time? Any questions before I pass the baton? Mike's in the back.
Get you a mic.
I'm also projecting that.
But we can't hear you on, you're going to be recorded and hopefully well edited, Mr. Bernstein.
I really appreciate the key misconceptions here because I've often thought about TE as this sort of peer-to-peer central piece, right? Like a utility, a smart city is trading electrons with your neighbors. That's how the economics sort of worked out, at least in my brain. So I was wondering if you could describe an example of a system that isn't peer-to-peer, that isn't just run by one utility, because it seems like when with this slide in mind, it almost becomes higher level, like the architecture concept that we're talking about, as opposed to like, I don't know, some of what you're describing also made me think about virtual power plants. You know, I'm thinking the aggregator would be the person that's kind of managing some of this. So if you could just describe maybe something, or am I on the right track?
So ultimately, I know way more about Texas's electric market than any other place in the United States because, well, I started there when I was at college. So in Texas, fully deregulated. So wires company owns the meters and the wires. Generation is all independently owned. Independently owned. They have to bid into a wholesale market, right? You can't own both, right? There's a wall between those. And then the person who actually sells the electricity is the retail electric provider. So think big giant apartment tower. Apartment A has retail electric provider A, right? B decided they wanted to go with Green Mountain Energy, so they're 100% renewable. Maybe apartment C has, I only want coal power. I don't know if there's an option, so I don't have a place where I get to pick. You go through and do that. So now you scatter that across everyone in the building. So now they have a retail electric provider who is not the utility, who doesn't own the meters, doesn't own the wires, right? They have to contract for all the services that they're providing to those apartments within that multi-story apartment building to be able to do it. So as you go through and look at that, now I have a third entity, right? In Texas, those are regulated entities to go through as an LLC. That's one use case, right? As you start talking about VPP in Australia, Mark Patterson will cover this with international perspectives, I'm sure. They'll talk about what they've done with virtual power plants within Australia, how products like PICE and Switched In and then Power Ledger help go through and provide that capabilities in markets that are upper parts of the penetration of distributed energy resources. So, hope that helped.
I can give you one more example because I'm actually working with a client now that's even more practical than that. Large retail, global, says, hey, I want to put rooftop solar on 50 of my buildings in the Sunbelt, but I want to transfer some of that power to the buildings that we own in an area where we can't produce as much solar. So they want to be able to use the transmission line to exchange energy in the transactive mechanism between multiple entities within your own company. And we're trying to figure out a way how we can make a market using the utility or the entity's transmission lines so I can produce solar here more than I can consume on any one building, put that in and take advantage of it somewhere else as a location-based transactive energy system. That's a real project.
I see real tagging opportunities for a company that sells tags. Farouk's next.
Yeah, thank you. So what I'm kind of missing in the whole discussion is the economics. Yeah, I mean, different pricing mechanisms, increased production, optimization, and all these play into the economics of these systems, which are also influencing the economy of the whole United States in one way or the other. And it was very simple in the previous times when you had just a bunch of operators and coal plants and so forth to have a unified pricing system. But now we're talking about different levels. And is there not, the second question is there not a need for a overarching, I mean, not authority, but someone, coordination on a political, economic level that can do a kind of like a Marshall Plan or something. And I know this is a democracy. It's much harder than in other countries, but yeah, that's my question.
Feature number 2.
That's it? Okay. Let me throw a little bit of a wrench into the mix here as far as transacting goes. And I'll point people at a project that was done during the 2009 energy, the ARRA program, the Pacific Northwest Smart Grid Demonstration. I was the chief engineer on that, my IBM team, working out and others. One of the things about transactive that a lot of people find confusing is it is not a prices to devices. And the way that we implemented that project is a good example. There are no markets in the Northwest. Okay, everything is done with bilateral agreements. There are no dynamic prices in the Northwest, at least at that time. What we implemented were transactive value signals that represented, as closely as you could, the cost of delivering electricity from a supply point, and it could be a bulk generator, or it could be some distributed solar farm, or anything in between, or rooftop solar. So the cost of electricity flowing through the grid. When you get to a boundary like a residential roof, that cost signal, which is varying depending on the needs at any point in time of that and the cost of supplying electricity to that point. If regulators wanted to have a dynamic price, they could take that cost signal and come up with regulatory models that just put an uplift on it. And so now that becomes a dynamic price signal. Other kinds of models can also be used. And what we did on the Northwest project is at the end of each month, the houses that reacted the most got more of a benefit. They got, in some cases, because there were 11 different utilities involved in that project. In some cases, they got a rebate of a certain amount. Depending on how much they were responsive. And, their responses depended on the kinds of devices that were involved in that particular utilities sub-project.
Ron, I'm going to close. It's like, for time?
Yeah, I'll wrap it up. So the key is, you don't need to have an overarching entity that's defining these transactive signals, because they're really being driven by the current state of the system. And a lot of times people are confusing them as price signals. And I think that to answer the other question, the transactive can implement a peer-to-peer model, or it can implement a centralized model. That doesn't make sense because that's what we already have, but some hybrid of the two, what's going to make the most sense. Like a microgrid that has a transactive agent that's operating a micro market. And then you can even go to campus level where you have a nano market in a microgrid on that campus out to devices that have agents that are responding and interacting with these. So you end up with a hierarchy of transactive entities that sort of reflect both the electrical physical layout as well as the business and ownership model of the equipment in the grid.
We're going to have to wrap things up on that. Yes.
So last thing, so to do a pitch for our friends at SEPA, one, if you want more information about grid architecture, there's a number of papers on the SEPA website that cover grid architecture. There's a grid architecture working group. There's also a number of use cases and histories of transactive energy that are available on the SEPA website. So thank you.
If you do have to leave early, I put out all the information about the council's symposium. Table that for you to grab one of those. Next up, we have Farouk Rahimi. Thank you.
Thank you. Hello, good afternoon. And yeah, I'm the last speaker today. I'm sorry? Oh, there's one more. Oh, okay. All right. I'm Executive VP at Open Access Technology International, headquartered in Minneapolis. I work out of a local office in Northern California, about 12 miles south of San Francisco Airport. These two topics were assigned to me to talk about what are DERs and what are the impacts on the grid, and then operational coordination in a high DER grid. Now, my first slide, this is something that already David Forfia went through, so I won't go through that again. The fact is that our industry is changing quite rapidly. We heard about what is going to happen 25 years from now, but a lot of things are happening right now. And as David pointed out, and this slide that I skipped showed, a lot of things we used to do in this industry, they're not going to work anymore with the changing scene that we have with energy transition and grid transformation. Now, the DERs, or distributed energy resources, they can be distributed generation, such as rooftop solar, small wind. They could be stationary storage. There could be electric vehicles, conventional demand response or load reduction, and even energy efficiency. This is what the distributed energy resources are, and they could be behind the meter or in front of the meter. Normally, when they are behind the meter, these are owned by the consumers, and you heard the word prosumer, a consumer that both can consume energy and produce energy put into the distribution grid. If you have rooftop solar, your meter actually turns backwards and puts the energy into the distribution grid when you are not home and the sun is shining and your consumption is low at the house. And they are operated, the behind-the-meter assets, by the consumers, may or may not be separately metered. In other words, my rooftop solar may not be separately metered from my rest of my consumption. In front of the meter, however, these are usually owned by larger consumers, like commercial industrial organizations, and they may be operated by themselves or by third-party aggregators. And you heard about aggregators from previous speakers here. Usually these are separately metered. Now, why are we talking about this? Is because the impact that these distributed energy resources have on the operation of the grid. Traditionally, the demand side was very inactive, and therefore the power would flow from central stations through distribution, to transmission distribution to the consumption. But now, all of these distributed energy resources, because of their variability, fluctuations, they have impact on the operation of the grid. Reverse power flows. In the traditional design of distribution systems, if the power was flowing out of my house, a relay would think there is a short circuit and would interrupt the flow of electricity. Whereas now, they have to really recognize that the power can flow in the opposite direction. There are voltage fluctuations that produce some issues for the grid operator. Phase imbalances, the free phases A, B, and C, and they could be unbalanced. You could have consumers on phase A having electric vehicles, on phase B having rooftop solar, and therefore there would be unbalance among the three phases. And one of the main concerns about operating the grid is to have the three phases more or less balanced, because if they are not balanced, they can lead to neutral currents and other issues that the distribution grid operators do not like. And of course, you have fluctuations in the frequency of the grid. Now, this is all happening if these distributed energy resources are operating without any coordination. And of course, you heard before about providing grid services and so on and so forth, and the answer is yes. There is also an impact on the bulk power. I'm not going to go through that. The answer is yes. All of these distributed energy resources can be leveraged to provide the grid services that are essential for the operation of both the distribution grid and the bulk power. But it cannot be done in a confiscatory manner. The utility cannot simply control these assets. However, there are programs where these distributed energy resources, in return for some incentives, agree to operate in such a way to not only not cause problems for the grid, but provide the grid services. Kay talked about some of those services in her presentation discussion. So they can provide these services for the distribution grid and also for the bulk power. You heard about some of the bulk power services such as frequency regulation, spinning reserve, and so on and so forth. Now, one of the most intricate services at the bulk power is frequency regulation. It has to take care of second-by-second fluctuations of the supply and demand imbalances. And the question was whether these distributed energy resources can be used to provide that kind of intricate service. We did an experiment from some distributed energy resources, a combination of electric vehicles and electric water heaters in Hawaii, and a control system in the cloud in our Minneapolis data center. So what would happen was that the grid operator in Hawaii would send a signal to the cloud, and that signal would be received and it will get distributed on the different electric vehicles in Hawaii that were plugged in. The system remembers or knows the state of charge of these vehicles, which one can be charged and discharged, and so on and so forth. So this setup was used to test to see if frequency regulation could be provided by these distributed energy resources. And a measure was used to actually measure the performance. This measure is something that PJM had developed for performance assessment of frequency regulation in PJM. It has several components, 3 components in fact: a delay, a precision, and a correlation performance, and a combination of those. When we measured the response of these devices that were located in Hawaii and would exchange information through public internet, secure public internet, with the data center in Minneapolis and then back to these devices in Hawaii, the performance was better than some of the conventional generation. I have some numbers in here. The accuracy, 97%, delay score 100, precision 90, and the composite score was 95.7. Whereas for conventional generation, these scores are less. So this was a proof that with proper incentive, you can have these distributed energy resources provide valuable grid services. Now, let us go back to the traditional operation of the utilities. That was saying until a few years ago, they would say if Graham Bell came today, he wouldn't recognize our communication system. But if Edison or Tesla came today, they would not only recognize our power system, they could even fix some of the problems. That is no longer true today. And the picture I'm showing in here is the situation before the proliferation of distributed energy resources and their use in operation of the grid. On the left side, you have the so-called IT or information technology. On the right side, OT. Now, the operation technology in a utility was mainly by the control center. They would have a network model, they have a state estimator, they would have systems to control voltage and VAR, they have FLISR, which is fault location, isolation, and service restoration, SCADA, supervisory control and data acquisition system, outage management system, and mobile workforce. And these were mainly dealing with assets that were owned and operated by the utility. The customer service, on the other hand, dealt with the customers, demand-side management programs, customer enrollment, the tariffs, metering, settlement, and so on and so forth. Now what we are facing is something in the middle. Consumers and third parties have some of these assets, EVs, PVs, photovoltaic, then battery energy management system, microgrids. They have contractual arrangements, as I mentioned, based on the incentives that the utility provides to them. And these contractual statements have to be respected. For example, if I sign up with you, you cannot curtail me between 4 and 6 p.m., for example, or you cannot curtail me during the weekend or something like that, or when I have an event going on. And in the middle, therefore, assets are no longer owned or operated, or owned by the utility, but based on these incentives, they are operated by the utility. So this results to a question that was asked before: how are all of these distributed energy resources managed? And this is where the term DERMS, or Distributed Energy Resource Management System, comes into play. And the right-hand side, we have Advanced Distribution Management System, and that is what normally the control room staff work with. So this is the trend that we are seeing in here, that DERMS, Distributed Energy Resource Management Systems, are used to enable incorporating distributed energy resources such that they are incentivized to help the grid rather than cause problems for the grid. And in doing this, one of the main things is to make sure, as opposed to traditional control rooms where they worried mainly about what is on the right-hand side, which is grid topologies, voltages, and so on and so forth. Now when they're using these distributed energy resources, they have to also respect all of the commercial arrangements and all of the things that are stipulated between the utility and the consumer. Data accuracy and timeliness are central in this unfolding paradigm. Aggregators are mentioned, that they are aggregating these assets, sign them up, and use them to provide grid services based, of course, on the arrangements that they have with these consumers. However, it is very important to make sure that these are all legitimate operations. I have two examples here. A recent example in MISO, Mid-Continent Independent System Operator Territory, where an aggregator was getting a lot of money from the market by giving lists of prosumers or consumers that he had actually enlisted, signed up to provide grid services. They would offer grid services that the probability of deployment is low, is small, and these are usually contingency reserves. You get paid for it, but unless there is a contingency, you're never deployed. And MISO found out that this particular aggregator had provided a list of consumers who had never signed up with this aggregator. And of course, they got fined $66 million. So we have another example in a utility in California where consumer switching took place, consumers moved, and the utility failed to inform the aggregators. And again, the penalty is about $1,000 a day per consumer. So these are some of the important issues regarding data accuracy and timeliness, information exchange. Security, we talked about before, we had previous speakers talked about privacy and data security. And of course, we have the issues of settlements, measurement, and verification. And so let me go to the next topic, which is operational coordination in this high DER grid. And this is very important. Kay showed you a different picture of various players in the emerging scene. Here I'm showing this in a different way. We have the consumers, prosumers, aggregators at the lower level, close to the grid edge. Then we have the distribution utility in the middle and bar power operation on the top. On the right-hand side, we are looking at the utility, which is in a deregulated environment with a separation between distribution operation and bar power operation. On the left, we are showing a vertically integrated utility. So all of these players interact with one another. And you also heard the DSO, distribution system operator, as a new entrant on the entity, which is really the traditional distribution system operator, which now takes on additional responsibilities. And those additional responsibilities include handling all of these distributed energy resource management systems, distributed energy resources through the DERGs. Now with that, when we look at distributed energy resource management systems, we recognize that based on this multitude of players in the field, we could have edge DERMs that are close to the grid edge. They are used by, for example, very close to the grid edge, like microgrid operators and so on. Aggregator DERMs. We have enterprise DERMs that are used by distribution utility to operate the system. And then we also have You heard about virtual power plants. Virtual power plants are aggregation of distributed energy resource management systems. Now, when these assets are aggregated by aggregators, if the primary purpose is for this aggregation of resources to act like a power plant, they are called virtual power plants. They provide energy, ancillary services, grid services, and so on. But there's also another use of these distributed energy resources when they are aggregated, and they are non-wires alternatives. In other words, these are used to defer the investment in some of the distribution assets. An example, in Brooklyn, Queens, in New York, they deferred the upgrade of a particular distribution substation by leveraging the virtual power plants as non-wires alternatives. The same thing at BPA. They also deferred or made it unnecessary to invest in a high voltage transmission line by implementing instead some non-wires alternatives which consisted of large storage assets on the two sides that would otherwise be a transmission grid. So the configurations that I mentioned of DERMS, this is really what requires all these different levels of DERMS among these different layers, coordination among their operations. And in this figure, I'm showing the various characteristics of different flavors of DERMS, enterprise DERMS, aggregator DERMS. In the rows, I'm showing the required capability, modeling, creation of aggregations and provision of grid services, scheduling, optimization, and so on and so forth. I won't go through all of these. This is an eye chart, but in the vertical columns, we see the difference between what are these capabilities are offered by enterprise DERMS, the DSO DERMS, aggregator DERMS, and so on and so forth. Now, the last piece that I want to talk about is this operational coordination among various entities, the aggregators, distribution utility, particularly bulk power. You heard about, or somebody mentioned, FERC Order 2222, which really mandates the grid operators under FERC jurisdiction to accommodate participation of distributed energy resources in their markets, to provide all of the services they are technically capable to provide. Of course, these assets are sitting at the grid edge. The market is operating at the bulk power, and distribution utility is sitting in between. So this participation of distributed energy resources in the bulk power market requires close coordination with the distribution utility, which is sitting in between. And this is something that is demonstrated in this diagram in here, where an aggregator tells the bulk power operator what kind of services they are going to provide, but the bulk power operator has to check with the distribution utility whether this would cause any problems for the distribution operation. If the distribution utility or DSO says, hey, this kind of participation in the bulk power market will cause problems for me, like phase imbalances and so on and so forth, then they can deny, and the bulk power operator will not accept the participation of those aggregation of assets in their market. So this is something which is really important in terms of operational coordination among grid edge asset operators, distribution utility, and the bulk power operator. And with that, I'll stop here if there are any questions.
Thank you, Farouk. Okay, I'm actually going to have whole questions, and let's let Jamie get to the last piece, so that you can all go. And anyone who wants to stay around for questions, we'll all be sticking around for a while to answer all the questions. So let's let Jamie get through. Come on up. Our fearless administrator.
Our leader.
Yeah,
Dale
he's
leader.
the leader.
Dale leader. Leader.
Thank you all for looking. So I am Jamie Colin. I am a power system engineer at PM&L. When it comes to the work with the council, I have a bit of a history there. So I really wasn't part of the council, wasn't really doing much work with the council as of about 2 years ago. What I was doing was reading all the papers and gaining information and learnings from all the hard work that they've done over the course of 20 years now. Happy anniversary to the council. So with that, I'm going to kind of go over, change from my research role a little bit here, where I talk about standards and interoperability, all those great things. I'm going to give you a little bit of a background of the council that didn't get covered and a pitch of why I found it valuable, and also, ways that you guys can participate and contribute. So recently, one of the first things that we took on when I became the administrator was to revamp the mission and vision statement of the council. It had been 20 years and things have changed, and a lot of their great work had already been adopted. And so we wanted to, while not changing the overall structure of the council, give an idea of what the extended focus of the council had become. Interoperability, we talked about earlier with the GWAC stack. We'd taken a good stab at that, or I should say the council had taken a good stab at that. Developed the stack, which has been referenced in many of the standards documents that I have read and continue to develop. And then also the transactive energy portfolio of work that they and PNNL have done had kind of grown into a being of its own. There's programs like the MIDAS program in California and some other activities across the country that are adopting some of the transactive methodologies and concepts. So in that sense, we had kind of not completed those tasks, but taken them to the level where the council should take them. Very much supplying the tools and capabilities, concepts, and innovation that folks would need to get to that level. So you see on the screen the mission and vision as we've updated it. I think one of the important things to note that you'll hear continuously going forward is the idea of the 3 Ds. So democratized, decentralized, distributed. Those are core to all the work that we're doing going forward. And the mission really now is about disseminating the architectural concepts. So not just transactive energy, not just interoperability, but making sure that we're giving folks the tools that they need to understand how those things can be applied. And so that's encased in this mission and vision statement that we revamped. So I just want to point out a few of the things that you guys may or may not have seen out there in the world. What's really interesting about this, you'll see Ben Franklin up there. The kickoff for the work that they've done, and I think there's a young Ambrosio in that picture, maybe still some red in his hair and so on. So they had an actor, Ben Franklin, lookalike come in, and they actually signed an interoperability constitution, which laid the framework for those initial documents. And then you see a picture of the GWAC stack on the right. The Smart Grid Interoperability Panel, many of you may know them now as SEPA. When they merged in, I think, about 2018, SGIP and SEPA merged. SGIP was started under some of the ARA funding, and what the idea was that NIST would have this funding. They would start an organization of folks with a bunch of working groups to kind of tackle the challenges of the forthcoming smart grid. It was mentioned to me at one time that it was insidious how many council members were the workshop chairs of SGIP when it first started. And a gentleman by the name of Robbie Simpson, who will be in our panels later, was a young man at the time, and he was the only non-GWAC member working group chair in that group. But
architecture working group chair for the first 5 years.
Yep, and there is still a grid architecture working group. So if any of you are SEPA members, you will always see a taste of the council at SEPA, whether you like it or not. You'll also,
Always chaired by Ron's.
yeah, and there's usually a Ron involved somewhere. We joke that we always have room for more Rons, not morons, more Rons. So GridWise transactive energy framework that you guys have heard about quite a bit today, and the transactive energy techniques are part of that, but there is many pillars to grid architecture. And so the idea going forward is that we disseminate these works. I put a link up there to our YouTube channel. We've modernized a little bit. We're sharing our monthly meeting panel speakers and presentations to the world. You can also see some of those great videos that we shared at the beginning describing what the council is. Take a look at those. And then also make sure you get access to these documents. The conversation came up earlier. What about regulators? They won't understand this stuff. And so you'll see in 2020, we revamped the decision makers interoperability checklist. Those are really great. They're just brief, quick questions that should be asked if you want to promote interoperability, and they can be understood for the most part by regulators. There's probably a few in there that are a little tricky and you might need to explain, but all these decision makers checklists and so on are really valuable, quick reads. And then the more complicated documents where we talk about practical guides to grid architecture. So please go ahead and check those out on our website. There's some of the older work that we mentioned already. I'm not going to go into details on that, but there is all these are linked. You can see the history of the council. And then we have some ongoing work products. So I want to make you guys aware of these. One product that I'm not going to mention in here is the future states document that Mr. Ambrosio shared with you. We're going to release that before the conference this week, and I'll share a QR code during that event, during the symposium, so you guys can download that document, give you the details that were worked out by Mr. Ron Cunningham, who's GWAC Emeritus and was unable to make it today. Upcoming, we have some work that's being performed for regulators, in fact, so grid architecture for regulators. Lorenzo Christov is leading that team. Kay Aiken, who you heard speak earlier today. I know you heard Mark Patterson's name. Somebody else mentioned, do you know Chris Villarreal? Yes, we do. He was also part of that document. This document is being reworked a little bit based on some feedback, and I think what's important to note about that is that that's what the council does. We don't just throw things out there and see what sticks. We work very hard to get feedback from all of you, and your feedback is invaluable in basically informing our documents and our recommendations, understanding the challenges that we're trying to address, and so on. So encourage you to get involved in the council. You do not have to be a member to participate. Some of the work that we're talking about right now, you saw the Sydney Harbor Bridge earlier today, applying those concepts to bridge back from the future. No, not back to the future, back from the future. The idea being if we envision a future system and we work towards that goal, rather than trying to patch and band-aid the system we have, we'll be more successful in developing the system we want, and in fact saving money along the way rather than having to repair band-aids here and there. This is happening two times a month, first and third Thursday of the month. If you'd like to participate. We also know that electrifying transportation is an important key component to the grid of the future. I personally work on a lot of V2G work, so I may have had some influence in recommending that we do this work. I think this will have a great impact on the transportation sector as they understand how those vehicles will interact with the utilities and electric grid. This work is basically based on some other work that we've done on concept models with SEPA. So if you want a preview of what that might look like and understand what a concept model is, go to the SEPA website and download that. I do believe it's not behind a paywall, but if it is behind a paywall, you should all be SEPA members anyway, and then it's free. Upcoming GWAC meetings. So this is the big ask. anybody that's here today, you will also have access to the GridWise Architecture Council Symposium, which is bridging back from the future. And so I would assume that many of you will be here on Wednesday and Thursday. Drop in and visit us there. In fact, it's a workshop type scenario, so not only will you get to learn, but you'll also get to give us feedback that will inform our upcoming work, including the Bridging Back document. Oh, there is a typo, 11th and 12th. Okay. Well, it was the 9th and 12th originally. So now you have to be there for 12 days of GridWise Architecture Council. And then we have we're really thankful to Chair Bernstein for hosting us. We'll have a face-to-face meeting in San Diego. You guys these meetings are open to the public, not the in-person part, but we will have a virtual component, and I'll go ahead and post a QR code so that you can get to the GWAC website and sign up to be included on our distribution list. These virtual meetings are also open to the public. You will hear some council business, but each one of those monthly meetings has a really engaging speaker. We've done a really great job over the past year and a half of having some fantastic speakers, folks from DOE, folks from industry, some regulatory folks, so really diverse set of speakers. I'd encourage you all to join those meetings, and if you can't join those meetings, visit the YouTube page. We do post those presentations on that site. And then I want to, before I go through the symposium agenda, I do want to let you know that the council is open for application. So there are 13 rotating council people. We almost always have at least one that is going to become council emeritus. They get the same rights and privileges to represent the council as anybody else. They do not have voting capabilities, but we do continue usually to engage with them. And so in that way, even though they fall off of the council, they still end up usually being strong contributors. But that does leave the position open for others. So if you are a thought leader in your specific area, and that doesn't have to be a utility or anybody specifically related to the electric system, policy folks, consumer advocates, buildings people, we need all those opinions. As long as you're a stakeholder of the electrical system, which it's pretty hard not to be if you use electricity, you can apply for council membership. As I said, we do want to emphasize that there is an acknowledged level of recognition that you have to have in your community to qualify, but I would encourage all of you to call for candidates. This says it's open. It actually opens in October. I think this is a dated slide. It will open in October, and your insights and contributions are valuable, so please click on the link. If you click on this link, it'll take you to the homepage, and there's another option where you can click on how to email the administrator and get added to the friends list. And then we have the symposium. So that's the 11th and 12th, yes. We have some fantastic speakers, including Gene Rodriguez, the U.S. Department of Energy Assistant Secretary of Energy for the Office of Electricity. So Gene will be giving our keynote speaker. If you've never heard Gene speak, it is something to see. I would say if he were running for office, I would vote for him, and I don't even know what he would run for office in, but I would probably still vote for him. So Gene is a fantastic speaker and can give us some insights into the DOE and their vision for the future of the electrical grid. We have some panels on grid edge, including the grid transformation. How do we scale all these activities at the edge? We'll have some policy and regulatory panels. We'll have Kay speaking about coordination and dynamics.
I'm only herding cats.
You're herding. Oh, well, you'll be moderating. You'll be moderating coordination and dynamics. And then on top of that, we also have some customer perspectives, which I think is really important to understand how we're engaging with the stakeholders for the electrical grid. So without those stakeholders and those customer perspectives, we don't know how transactive energy might work. We don't know how people will electrify their systems. So all of these things are really important to have, and we look forward to seeing everyone at the symposium on the 11th and 12th. It's one floor up, so all you have to do is go upstairs and come and visit with us. You'll also have a chance to workshop and visit with the panelists and the council members as we all come up with these solutions, right? We're going to come up with some good ideas to build out the grid of the future. Thank you all for coming, and I guess we have some time for questions still.
Round of applause for all our speakers.
We only have a few minutes because we are trying to get ready for the next group, so maybe 2.
Yeah, let's, I don't mind ask a question. Anybody other than Myron?
Please,
We'll come back to Myron. Anybody else?
I am delighted to say that I was invited to speak at the panel at 1 o'clock Wednesday. However, if you go to your REplus app on your phone, you won't be able to tell that's when you want to test. And I'm wondering if Jamie can get the people who write the software behind the REplus app to actually do it, because I don't know how many you're doing the speaking and
So the website where you can pick up one of those flyers back there that I printed out this morning that has everyone and all the slots and where everything is. The person you talked to back there is Leslie. Raise your hand, Leslie. See if you can help fix that if you can. Any other questions? Is it beer 30 yet? I think so. All right. Big round of applause for everybody. Thank you for There's this question. Let me just see a thumbs up, thumbs down, thumbs neutral. Was this valuable? Thumbs up? Thumbs up? Okay. Good. Thank you. All right. Enjoy the conference.